Hello and welcome to lecture 20. In this lecture, we are going to talk about the multilayer perceptron. Essentially, we are beginning with something that's known as neural networks today, one of the most popular machine learning models, and also called artificial neural networks. These are popular machine learning techniques that simulate the mechanism of learning in biological organisms, like the human nervous system, for example. So that's what neural networks are. We are going to begin talking about them by first talking about the multilayer perceptron. And why is that? Because we understand perceptron really well. And so we're going to build on that. All right. And then we'll talk about approximation versus generalization and derive the neural network, but just like begin with the definitions today and talk more about it in some of the lectures that are coming up. All right. A quick recap as always. So last time we talked about unsupervised learning. We began with similarity-based methods, and we found out that unsupervised learning is one of the important aspects in there, especially in cases where we don't have like label data, we don't have an answer to the question that we're trying to answer, like ask essentially, but we have some kind of like structure to the data. We have some kind of organization to the data. And based on that, we looked at two important techniques. The first one was k-means clustering, and the second one was the Gaussian mixture model. K-means clustering utilized these clusters by identifying certain centers in the data, and then we used an alternating algorithm called the Lloyd's algorithm to solve that. Next is the Gaussian mixture model, or the GMMs, which focused on the probability density estimation. And utilizing that, we figured how we can kind of get patterns in the data, discover patterns in the data, and then we looked at something that's known as expectation maximization algorithm that was able to achieve really good results. So this was an algorithm that was kind of bootstrapping itself to a solution. So those are the two techniques that we focused on last time, and today, as I said, we are going to talk about neural networks. Okay, so let's begin. As I said, neural networks are biologically inspired. Essentially, this is how it started, although the neural networks of today are way different from the biological organism's nervous system. But think of the human nervous system. It like this is the picture that's shown here. And so this nervous system contains cells, and these cells are referred to as neurons. And then these neurons are connected to one another with these like axons and dendrites. And the connected region between these axons and dendrites is referred to as synapses. Again, I'm not like going into the details of the technical terms. What I'm saying is that this biological mechanism is simulated in certain ways in the neural network, because that also comprises of these computational units that are sometimes referred to as neurons, and that's why that's where the name comes from, the neural network. All right. And again, even in the neural network, similar to like these connections, we have the connectivity, but it's like in terms of weights and other things. So we will discuss that, of course. And then a quick peek at the history of how neural networks began and where they are right now. One significant like beginning, although we can like date it back to around 1940s, but one significant beginning was the Rosenblatt perceptron that began around 1958, and it became more popular with multi-layer perceptrons around 1960s in the end, because we got something that make the use of like fitting functions easier. But then for a long time it disappeared. For a very long time it disappeared until it like reappeared in the late 80s and maybe early 90s. And in the early 90s it appeared because there was this like there was this multi-layer perceptron and generalization and ability to fit well with back propagation. And then finally in 1992, statistical learning evolved. From the statistical learning perspective, the issue of like overfitting was addressed. And then again, for some time, neural networks lost its popularity. Finally, with the advent of support vector machines, they were revived. Support vector machines is another very robust technique that we are definitely going to cover in this course. And once support vector machines came into picture, then by combining that with a nonlinear transform, the neural networks became really popular again. Eventually, in like 2006, around 2005, 2006, new training algorithms and the concept of pre-training the neural network became more and more popular. And around 2010, like more specific 2012, the classification of images was made possible, and the classification of images was done like really well, and that is when the neural network took off. Application to vision is another important achievement of the neural network. It inspired like a surge in neural network applications. And now, at like at present, like in the 2020s, I would say this timeline just ends there. But of course, now the popularity is rising as much as you know, more than me. And the most important reason behind the popularity is the humongous amount of data that we have, and the amount of um, data and the amount of information that we have, and the fact that neural networks can be, and we'll see how, can be made to utilize that data in a very useful manner. And that's why this has like kind of gone up. This has surged the use of neural networks. So we will also address some issues that pertain to neural networks going forward. And of course, the foundations that we built sometime earlier in the course are going to help us achieve that. But first, we're going to look at like where exactly we begin. And we are familiar with the linear model, of course. All of us are familiar with the linear model. So you can think high level that these neural networks are nothing but a combination of the linear models in a cascaded manner. And another small thing before we move on about neural networks is, again, as I said, we were saying that these are biologically inspired, but this is like to not like take it literally, because neural networks of today are no more biologically inspired. They are driven more by engineering. This is similar to the example that we started flying. So we created these like airplanes and started flying by seeing birds flap their wings. But now you don't see airplanes flapping their wings. So what matters now is the engineering success, and it's similar to the neural networks as well. All right, so this was like little bit of a background, and what we are going to do next is we are going to start building something that's known as the multi-layer perceptron, and let's begin with the motivation. So here is the motivation, the XOR function, which is the motivation. Now, if you look at the XOR function, it's nothing but like these two lines crossing one another, right? And there are opposite regions and they have the same classification. Like this region and this region has the same classification, and this region and this region has the same classification. So if you think about it, this is my target function. This entire, like these two lines together, is my target function, f of x. Now, in terms of the function, like the function itself, this looks like a simple target function, right? And like there are other like simple, if you think about this is like a simple target function, but I don't think a perceptron can achieve this. I don't think a perceptron in its original form can implement this. And there are other simple functions which the perceptron is unable to implement. Of course, you can argue that we can do some kind of a transformation here, right? A nonlinear transform, but then that will also lead to some very complex transformation. So, based on this idea, how about cascading the linear model? How about cascading the perceptron itself? Because I can just by looking at the function say that I can maybe break it down into some smaller problems, and this applies to any complex problem that I can go and break it down or decompose it into its simpler versions and then put it together. So the goal for today is to derive the multi-layer perceptron, and the neural network is just like this extension of the multi-layer perceptron, so just like made more convenient to run algorithms and other things, but that's where we begin. So how do we begin doing that? We are going to begin doing that by using the XOR function. Okay, so as I said, I'm going to make this really simple by breaking it down or decomposing it. So this is what it looks like. Now, if you think about it, this is my target function f. And if I take this and this separate, so this one is here, just like this one perceptron, and then this was the other one, right? And what are these representing? So if I'm representing this by h1 of x and this is h2 of x, so these are like two different hypotheses, and I just broke them down. That's it, right? So what happens to like how do we express this decomposition mathematically? Well, mathematically it's expressed like this. And why is that? let's look at it. Why is that? Now notice these positive regions. Like let's say, notice this one. If we notice this lower region, this is like when my H1, which is this, is positive, but my H2 is not positive, right? This is what this region is representing. Now, similar to that, what is this region representing? Now, this region is representing when my H2 is positive, most likely my H2 is positive, but my H2 is, let's say, +1, but my H1 is not positive, or it's -1, right? And so my final hypothesis should be a combination of each of these, which in turn is given by this equation here on the right hand side. So notice the first term. This first term is saying H1 is positive, not H2. The second one is saying H2 is positive, but not H1. And then I'm saying this has to be like an OR of each one of them, like this plus this. So essentially, this is what this is signifying. Either this or this will give me the positive region, right? And together, like each one of these terms is an AND, like I'm talking about the Boolean AND and OR. And so this means H1, not H1 and H2. Or this one here means H1 and not H2. All right. So here we figured some way of representing mathematically, of course, pictorially we could, mathematically the target function using AND and OR operators. So we could decompose it into these like simpler hypotheses in order to get the perceptron. All right. So let me first define these Boolean functions for a more general sort of situation, and then go from there, because we need to understand why do we care about these AND and OR. So let me figure that out here. And generally speaking, or mathematically speaking, for these points x1, x2, and so on up to xd is, so it's +1. It's going to be positive if all my inputs like x1 up to xd are positive, right? So I can say that this is +1 if x1, x2, and so on up to xd, they're all equal and positive, and -1 otherwise. Right, for the rest of the cases, I don't care, because then it's going to be negative. This is how the AND Boolean function definition works. All right, what does the OR function definition tells us? Well, x1, x2, and so on up to xd. Now, this is going to be -1 if my x1, x2, and all of these are -1, and it's going to be +1 otherwise. All right, so this is like the basic definition of the and the OR function. And why are we so concerned about this definition? Why do we care? Well, if you think about the and the OR functions, they are nothing but perceptrons themselves. Okay, so how does that help us? Now remember how we depicted my target function. This was like h1, h2 plus h1, not h1, h2, right? And so this is nothing, and there is an and here, and an and here, and there is an or here. And then these h1 and h2 are themselves something. And so that's why I care, because I know that I can use these ands and ors as linear perceptrons, and then maybe utilize them. So how do we do that? Let's consider this example where we are looking at 2 inputs. And let's look at this example, because this is going to help us in doing a visual representation of implementing and or by a perceptron. But even before we start doing that, I just wanted to go over some kind of a visual representation, or I would say an alternate representation of like a hypothesis as such in general. So because this is going to be the basic building block going forward. So for instance, for h1, which if you remember is simply h1 of x is the sign of w1 transpose x. And one way to kind of write this is, let me show you. So we have these nodes that represent my input, which is going to be x1, x2, and then the augmented one. So we are assuming that that exists And then these arrows will represent some kind of an input. And this goes into my sine function, which is this, right? Sine function, which going forward, I'm going to like use something like this. And then you get your final like h1 of x in this case. So what is all this? Now these nodes, these circles here, these are like these output values using an arrow. Like basically they output some value on this arrow. This is what this means. And then the weight on an arrow is multiplied to this output. So here on every arrow, there is going to be a weight, which means here in this case, it's going to be, because this is like W1 transpose X, and the components of that are going to be here. So like maybe W1, W2, whatever we are, this within this vector, whatever those are. And similar to that, we can have a similar visual representation for H2 of X. And as I said, now these weights on each of these arrows will be multiplied to the output of each of these nodes. And then that is passed to the next node, which in our case is a sine function. So if there is this like sine function and everything is coming to that sine function, then everything needs to be summed up and transformed by that sine function. And of course, we'll talk about other functions as well that can be applied there. And you get some output. All right, so why were we talking about this visual representation? Because we want to see the implementation of the and the or, because we just figured that that's nothing but a perceptron. And how can we do that? What choices of weights essentially can we come up with to get this implementation of and or? All right, let me use another slide. So we have again the same 1, x1, x2, all right? And I don't know what the weights are going to be because we have to think about based on my output. And so this is like my sine, and my output is going to be an and on x1 and x2, assuming that we just have like two inputs in this case. And this is just to like understand. So how do we get the weights such that my output, the and of this is going to be like +1? What could be one way of doing it? Well, if we have these options of like adjusting these weights somehow, maybe if this is like a +1 and this is a +1, then I have to adjust like this W0. And by the way, this is like the weight for the W0. Maybe I forgot to mention, this is like the entire vector, and this is W0, W1, W2, the components. All right, so this W0, by the way, has to be like within like less than 2 at least, like if this is to be negative, so that we pass this like 0.5 here. So for instance, if I'm like choosing something close to like -1.5, let's say, right? So this is the only way to get +1 here, because like this is going to have 2 minus 1.5, because I'm going to sum them up. Let's say these are the values that they have passed. So essentially what I'm saying here is that this here is nothing but the sine of -1.5 plus x1 plus x2. Just like a choice of certain weights, and of course these could be something else as well. But this is just demonstrating that we can implement the AND function using a perceptron. Similar to that, I can do something with an OR, right? So again, 3, and I'm assuming I'm working with only x1 and x2. All right, and then we'll have these inputs that go into my sine, and then I get an OR. So depending on the definition of my OR here, remember, this is like -1 if x1 equals x2 equals -1. For all other cases, it's +1. So what are those other cases? Basically, I can say that there is one way to get a negative here if like my w's are all negative. So let me just avoid it and get anything here which is positive, and let me take this, right? And so this here is nothing but the sine. This is like the output of this is sine 1.5 plus x1 plus x2. All right. So what we figure here is that we can represent and OR using a perceptron. And why was this important? This was important because and OR were the important integral parts of my f of x, which was representing the XOR function. So we can represent the entire f of x only by using a perceptron implementation. But how can we do that? So there are like multiple steps to that. So let's begin with, because we said that f of x is the OR of two things, right? Let me go back. Where is f of x? Here, right? My f of x is the OR of two things. And what are those two things? Well, those two things are my h1, h2 bar plus h1 bar, h2. So let us assume we already have these quantities with us, right? And so can we do something about it? Well, let me do that something about it. I'm going to do an AND on it, right? And so this will always stay because that's the bias term, and h1 h2 bar, and the other is, I think, the flip, right? h1 bar h2, and we are going to pass it through some sign, which is the OR of these quantities to get my f of x, right? So I'm going to do the OR implementation, and we just saw how to do that OR implementation based on some adjustment of weights. So I'm going to stick to that value only because I know that I'm doing an OR here essentially. And so this is going to be plus 1.5 plus 1 is enough. No need plus 1.5. So that's it. That's about it. All right. So what else? Now we have some information about like how to get these H1 and H2s here. And what is that information? Well, I know that this like H1, H2 bar or H1 bar, H2 is essentially an AND of these two quantities, right? And we know how to implement an AND. And so that's exactly what I'm going to do. So let me have another like sort of, and I know that these ANDs can be calculated using H1 and H2. So I'm going to utilize that, right? And just now we learned how to implement an AND, right? We just learned that. So let me try doing that. For example, let's implement this AND, H1, H2 bar. So H1 is fine. It's coming as it is. And this guy is also fine. What is this H2 bar? Well, I can control that because all I have to do is whatever input is coming through this like edge from this node H2, I just need to negate it. So just like flip it, multiply it by -1. So that's what I'm going to do. -1, and then this was +1, and in my AND this was, remember, -1.5. So I'm not going to change that. Now similar to that, I can do something here, and let me denote it by a dotted line. Okay, I could have used another color, but I'm just scared of using too much technology here because sometimes this becomes weird when I try changing colors. All right, the important thing is the weight on the edges, which is -1.5, and then this is H1 bar. So let me negate it, and the rest stays the same because I know how to implement my OR. Oh, sorry, an AND. So this layer had the AND. Okay. Now all of this is good. I am here where I have one H1, H2, and to implement f of x, we still need these H1 and H2. And from where can we get them? Now, since H1 is sine of W1 transpose X, H2 is sine of W2 transpose X, which are perceptrons themselves, we can further expand H1 and H2 to obtain the overall graphical representation of f beginning from my basic input, which was my X, right? So let me do that, the original perceptron. All right. Okay, so how do we get the input? The first W1 transpose X, remember, H1 is the sine of that, right? And so let's see how we are going to get that. This is H1, right? So the inputs, let me take from here to here. And of course, these are going to be replaced by the sine function once I have them implemented, because I know, for example, for an AND, for an OR, what is the sine function, right? So these ANDs will be replaced by the sine here, right? Of course. And the same thing will happen here because H1 is no more that, rather it is like the sine of W1 transpose X. So maybe like these solid lines here are W transpose X, but then we need to have a sign in here. Similar to that, let me have the dotted lines and the arrows, of course, and the weights on them are going to be, this was W1, then this needs to be W2 transpose X, right? And let's see. Now, this is it, right? This is the implementation of f of x. Eventually, I'm going to get f of x out of these like multiple layers. Now, what we've done here is we have cascaded perceptrons one over another, like layers to capture all the functionalities of my f of x, or to capture the intricacies of the outputs. All we needed was to be able to use these perceptrons to capture every aspect of f of x. We just like broke it down into like smaller pieces and then put them together. So this entire structure is something that's known as the multi-layer perceptron, or also in short known as MLP, right? And all we need here is to be able to get the exact weights to accomplish this goal of like representing a certain function. Now, few important observations here are, and by the way, this like set of nodes is known as the input layer. This wasn't super evident. And this is the output layer. And all inside layers, this one and this one, these are the hidden layers, and we'll talk more about them going forward. So now coming back to the issue of being able to apply weights to accomplish this goal. So how do we get the weights? At first, there are a few observations about this. The first one is that this last layer is an OR. The output layer is an OR. This is an OR of the positive regions, because like each of the regions are coming in and we take an OR of that. So if we add more positive regions, we can have more inputs. So we can have like more nodes here. So this is like observation number one. And so the number of nodes is equal to the number of positive regions in F. Now the number of nodes here, right? So the number of nodes equals number of positive regions in F. Of course, we have like the bias node, but like apart from them, that's the first observation. And then the number of nodes in this layer here, right? This, like the second layer, or sometimes even it's known as the first layer, but like if we are counting input layer as the first one, then this is the second layer, otherwise this is the first one. Regardless, this layer is representing the hyperplanes, or the number of perceptrons we need to decompose my f of x, right? So essentially my final perceptron has, or this multi-layer perceptron has 3 layers when I'm not counting the input. And all we're doing is we are taking OR of ANDs. And this is sometimes in computer science referred to as my DNF, which is the disjunctive normal form. And we can implement any Boolean function as an OR and AND. And in practice, we don't care about this because like we have more complex target functions to kind of like we use this methodology, of course. And so because we have like more complex target functions, so we have to do some kind of modification to this like generic multi-layer perceptron in order to be able to apply it to some real world problems and real world functions. Because if you think about my f of x, it was pretty straightforward in the sense that I could break it down into these logical forms, or these Boolean forms. So let's like look at it in the next video, when I'm going to talk about, by using this 3-layer perceptron, then I'm going to build something that's known as the neural network.